In this example, we're given a simple single loop circuit that contains an inductor with 100 millihenry inductance and a single current source, and that current source is providing not a constant current, but a current that follows this particular equation. And what we're being asked to compute is the voltage, which is here, the power and the energy. These are the power and the energy. Of course, these are direct implementation of these equations. For purposes of simplifying passive sign convention, I'm going to assume that the I is here and that's the V, so the I is hitting the positive for these currents, so everything you see in here will be just replaced by the positive. Okay, so now all we have to do is to compute the V of t is just basically multiply the value of L, which is 100 millihenry, which I'm just going to write it in here. It's 100 millihenry times 10 to the negative 3, which is simply 0.1 Henry, basically. That's what it is. Okay. Anyway, you can substitute 100 millihenry or 0.1 Henry. I'll just keep it at 0.1 Henry. Okay, so we go on from there. So all we have to do is just based on this equation is just multiply 0.1 times the derivative of the current. So we can just go ahead and say V of t. Well, what's the derivative of 0? That's 0 for t is less than or equal to 0 seconds. Okay, what's the derivative of that? So let's take a look. What I'm interested in is I want to multiply 0.1 times 10, okay, times t e to the negative 5 of t, and what I'm interested in is the derivative of that. Of course, these two here are 1, like 0.1 times 10, so what's left is just I need to take the derivative of that. And of course, the derivative is just simply 1 times e to the negative 5 of t, and then minus, I believe it will be 5 t e to the negative 5 of t. So if we take e to the negative 5 of t out, you're going to end up 1 minus 5 of t. So all we have to do is just write it in here, e to the negative 5 of t, 1 minus 5 of t, and that will be for t is greater than 0 seconds, and that will be in voltage in here, and that will be of course in voltage in here. All right, so it's just a simple derivative, that's what it is. Okay, all right, so we figured out what the voltage is. Can we figure out what the power? Yeah, simple. P, well, what we need to do is I times V for this particular range, that will be 0 for t is less than or equal to 0. What about the second range in here? All we have to do is just multiply these two together. So if we multiply these two, what we end up with is 10 times t times e to the negative, I believe, 10t, 1 minus 5 of t. Okay, that's for t is greater than 0, and that actually will be in watts. Okay, well, how about the energy? W is just simply half of L times I squared. Well, I squared also have ranges, so all we have to do is just figure out what half of L is. I'm just going to multiply 0.5 times 0.1, and that's simply 0.05. Okay, so what we need to do in order for us to compute this is just simply, well, 0 squared is just 0 for t is less than or equal to 0. For more than that, what we have to do is just multiply 0.05 times 10 t e to the negative 5 of t, and the whole thing squared for t is greater than 0. Of course, we can compute this here. We can substitute it. For example, it will be 100, like 10 squared, it's 100 times 5. That will be just simply 5. That's 2 squared e to the negative, I believe, 10t. That's for t is greater than 0. So I can substitute this in here, okay, by that particular value. That's basically will be in joules, okay? That's basically it. All right, so we figured out the current, the voltage, well, the current were given to us, the voltage, the power, and also the energy. So let's take a look at a plot of them, of these. So I have done in here is I plotted all of them and I cleaned up all the equations so you can see them. And what we have in here is the following. So initially we were given the current source, so the current in here. So what happens is the current initially is 0, and then based on this equation there's some sort of a peak in here, and then it goes down, and that peak happened to be at 0.2. You can compute that peak either from looking at the graph, or you can compute, well, when with the maximum t, all you have to do is just tell me di of t divided by t of t equals 0. So what we have to do is just take the derivative of this here and set it to 0, and we'll figure out the exact t. Okay, so and you can compute it, and you'll end up that that value will be around here, like 0.73 or something like that, and 0.2. So that's the maximum amount of power. So let's take a look at the voltage. So what we see in the voltage wise is it was 0 before, and then at some point afterwards it becomes something similar to this, and you see it actually drops below 0 and then goes above 0. So there's a point at which it actually crosses 0, and it just happened to be at the same time as the maximum V in here. And again, let's take a look. This is an inductor. There shouldn't be any sudden change in current. There's no sudden change in current, so that's fine. Okay, we compute the power, so let's focus on the power a little bit. So this is basically the zero line, and as you know, if the power is positive, that means that particular inductor is actually consuming or storing energy or storing power, and when the power is negative, which is here, you'll see that that particular inductor is actually releasing that energy or releasing that power. And that's exactly what you see in here. It's at 0.2. What happens, like, it reaches some sort of a peak, it basically stores all the energy and then it starts to give it off. And that's what you see in here. So the energy actually goes to this particular value and we can compute it. Okay, all you have to do is just substitute 0.2 in here and you'll figure out that exact value, and then it goes all the way down back to 0. Again, what we can do is we can actually take basically before 0.2, we can compute the power, we can figure out this value, and then after the 0.2, which they should be equal because it stores energy and it releases all of that energy. So let me do this very quickly. So what I will do is I'll just say, let's take the integral of the power between 0 to 0.2 just to figure out the area that is actually trapped in here, just to see what it is. Hopefully we'll get this particular peak in here. Maybe this is 0.02. This is in joules, so maybe 27 millijoule or so. So let's compute that. That will be 10 t e to the negative 10 of t, 1 minus 5 of t. Okay, so you'll have to do these integrals. You can actually plug it into a calculator or whatnot. I have done it. There are tables where I will help you with these integrals, or maybe you can open it up and see it. It's not really that difficult. And what you will end up with is 27.07 millijoules. Okay, and of course you can do the same type of analysis from 0.2 all the way to infinity for the same equation, t e to the negative 10 of t, 1 minus 5 of t, and you should be getting exactly the same value but in the opposite sign, because this is the amount of energy that is being released. So you go to 0.2 to basically 27 millijoules, and then it releases 27 millijoules. You can do these calculations, do these integrals, and double check that this answer is correct, which it should be.